Alright, we are back. This is part 4 of the intake drum roller project for the Stellar Robotics 2018 CAD class. So in the last video we put in the bearings and the shaft, and we started putting in drive components. We located the pulley and the end caps for the drum roller, set some spacing up for that stuff. We also modeled the belt. The spot that we left off at was we left the gearbox unconstrained in this axis. So we've got to locate the gearbox in this direction. So, and then in addition, we've got to model the actual mounting structure for the gearbox itself. So what we're going to do is we're going to bring some sheet metal plates off the top of this gearbox, and we're going to bend it down, and that's going to catch the mounting holes. Now we're going to do one on the top and we're going to do one on the bottom. Now there's only two mounting holes, so there's one mounting hole here and there's one mounting hole down here. This other corner up here, this is actually one of the threaded holes that holds the whole gearbox together, and we can't use this for mounting the gearbox itself. So we've got a mounting hole here and a mounting hole here. We have two mounting holes. Now if we were to just bring a bracket off of this structure and down and mount to one mounting hole here, and then have a different bracket on the bottom mount to this mounting hole here, we'd have a lot of rigidity issues and it just wouldn't be that strong. So what we're going to do is we're going to bring the top one out and down, and it's going to come all the way down to the bottom, and we'll have a hole for the shaft, and basically it will capture both of these holes. And then the bottom one will also do the same thing. It'll come out and up, and it'll sit just inside the top one, and it'll also catch both holes. So we'll have two brackets kind of overlapping on the face of the gearbox, and both brackets will hold both holes. So that'll give us quite a bit of strength, and we'll add some flanges and stuff, and I'll get to that once we start modeling this thing. So with that in mind, we know that we're going to make these brackets out of 1/16, so we're going to have a 1/16 inch thick piece of sheet metal on the front, and then we're going to have another piece of 1/16 inch sheet metal on the front. So there's going to be two pieces of 1/16 inch sheet metal stacked up on the front of this gearbox. So that's going to give us an 1/8 of an inch of thickness. Now in addition to that, we will probably use a socket head 1032 screw to mount the gearbox. We could use a button head, however I prefer to use socket heads where I can. In a couple of our previous projects we've used button heads just for looks or convenience. However, for mounting a gearbox, if I can use a socket head, I would prefer to use a socket head. And in this case, that's what we're going to do. So the head height for a number 10 socket head screw is about, well, it's the same as the diameter, so it's 0.19. It's about 3/16 of an inch. You know, so if we think if we say it's 2/10 of an inch or something, we'll be safe. So what we want to do is we want to make sure that with an 1/8 of an inch of aluminum on the front of the gearbox, and then 2/10 of an inch or so of screw head sticking out, we want to make sure it's not going to hit anything. Now down here in this corner, I'm not worried about this corner because I'm trying to find an angle that I can show. It's going to clear the pulley. Nothing's going to run into the pulley. Everything's going to be clear. Up here, however, we're kind of right on the holes here and the belts here. So if we get this gearbox too close, the screw eventually would hit the belt. The belt could rub on the screw. Now it doesn't look like we're in any danger of, use the measure tool here. It doesn't look like we're in any danger of the flange of this pulley itself hitting. However, we could hit the belt. So how are we going to locate this pulley on the shaft of this gearbox? Well, we're going to use one of those hex spacers in here. That's how we're going to space this out. So if we just kind of loosely butt this up against it, and we measure, use the measure tool, and we go from the face of this gearbox to the belt, we get 0.161 inches. Now basically we would need 1/8 of an inch, and then we'll say 2/10 of an inch, so 0.125 plus 0.2, so we need 0.325 at least. Now in addition, I want to point out one other thing. We've got the belt nicely centered in these pulleys, however there is a little gap here, so during operation this belt can walk back and forth a little bit. So the closest the belt could be is not actually where it is right now. The closest the belt could be is butted up against this surface. So if we actually measure from the front of the gearbox to this surface, we get 0.128. So we need 0.325. So basically we need another 2/10 of an inch. Now we're gonna have to use spacers in here. And the spacers come in 1/8 inch increments, with the exception of the 1/16 one. So basically we can get 1/16 inch increments. Ideally we'd like to not have to stack up a whole bunch. So I think what we're going to do is we need 2/10 of an inch more than this. I think what we're going to do is we're just going to use a 1/4 inch spacer in here, and that's where this gearbox will live. And wherever we decide the gearbox is going to be, I mean, it can be in any position we want, and we'll just design the brackets that are going to hold the gearbox to hold it in the right position. So what we're going to do for now is we're going to go up to the Constraint tool and attach a mate from here to the hub of the pulley and set that to 0.25 inches and click Apply. So that'll set this gap, and then later when we add all the fasteners and stuff, we'll actually add an actual spacer in there. So let's go back to our measure tool and just verify that that did what we wanted. So from the face of the gearbox to this surface here on the inside of the flange, we have 3/8 of an inch. That's 50 thousandths more than we needed, but we did that because we wanted a nice fractional number for this spacer, and a little extra length is not going to hurt anything. Now we could move the gearbox back a whole bunch, but the reason we don't want to is we don't want to put load all the way out the end of the shaft if we can help it. Ideally, you want to keep the load up by the gearbox where this shaft can't flex and it can't put stress, as much stress, I should say, on the bearings and the gears inside the gearbox. So if you can load a gearbox closer to where the bearings are, and the bearings are just right here, you should. So that's what we're trying to do here. And then we'll probably do it in this video here shortly once we design these other brackets. We're going to use a shaft collar to just hold this on. Oh, we'll talk about that when we get there. But for the moment, let's model these brackets that are going to hold this in place. So all right, so let's measure a distance here. So I'm going to use the M key. I'm going to measure from the face of the gearbox, which is where the end of that flange is going to be, and we're going to measure to this outside face. So we get 2.085, and we're going to kind of do the same thing we did here, right, where we don't run the plate all the way out to the edge. We're going to offset it in 1/8 of an inch. So 2.085 is our number, and then we'll subtract 1/8 of an inch from that. So what we're going to do is we're going to just model a rectangular piece of sheet metal to go on top, and then we'll add the flange down to capture the motor. So let's go up to New. Let's pick sheetmetal.ipt and click Create. Let's get a 2-point center rectangle and center it on the origin. Now we're going to make this 2 inches wide, which will be the same width as the bearing block. It's just a convenient width. VersaPlanetaries mount nicely to 2-inch wide surfaces with a little extra room to spare. You'll see once we put it in the assembly, but it'll look about the right size. So 2 inches wide, and it's going to be 2.085 minus 1/8 of an inch. And that's our plate. Yeah, that should do it. Okay, so finish the sketch. We're going to go to sheet metal defaults, uncheck use thickness from rule, and type in our material thickness, which will be 1/16 of an inch. Click OK there. Go to the face tool. It automatically selects our region because there's only one region. I'm going to flip the offset. Should be okay. They changed this dialog around in Inventor 2019, so if you guys have updated already, we talked about it in the class session this week. If you guys already updated, this dialog will look a little different, and you'll actually have 3 different buttons that show different directions, and you can select which one goes away from you in this view. This is not a super critical step, but I do it just for consistency. So next we're going to pick, actually no, we're not going to do that yet. Alright, so now we got to figure out, basically the bracket's going to be 2 inches wide, right? So it's going to stick out on either side of the gearbox a little bit, which is fine. That doesn't hurt anything. We also want it to stick out on the bottom by the same amount. So basically what we want it to do is we want the bracket to extend past the center line of the shaft by 1 inch, right? So it's gonna, the bracket's 2 inches wide and centered on the gearbox. So it'll be 1 inch on this side of the center line of the shaft and 1 inch on this side of the center line of the shaft. That should make sense. And then we also want it to be 1 inch below the center line of the shaft. So what we're going to do is we're going to use the measure tool to measure from the top of this plate to the center line of the gearbox shaft, which is this this work axis. What is this called? A work axis. Yes. So it's 1 1/4, which makes sense because the whole thing's 2.5 inches high and the gearbox is centered vertically. And then we're going to add 1 inch to that to bring the edge of the flange down. And that's going to be the length of our flange from the underside of the bracket. I'll show you guys how to change that option here shortly. So it'll be our overall flange length, or our important flange length will be 2 1/4. All right, so let's go back to our sheet metal part. So when we were just looking at that there, this is the direction that this bracket is going to be. So if we're looking at this view like this, this is the orientation the bracket's going to be in. So the flange is going to be down. This side here is going to be the bottom that will mount to the top of this structure right here. So we need to use the flange tool up here on the ribbon. We're going to click this bottom edge. Now you'll notice if I press F6, it'll take me to the home view. You can also press the little house. We're rotating, we're looking at this edge right here. Alright? And then we said our flange length was 2.25, but there's a very important fact there. That distance is measured from the underside of this plate. And with our current settings here, we're measuring from the top. So it's 2.5 or 2 1/4 inches from the top to the end of the flange. We want 2 1/4 inches from the bottom to the end of the flange. So that's going to be under height datum here. That's going to be bend from the intersection of the 2 interfaces. So click on that. The bend position being flush to the end of the plate. This is flush. That's what we want. The bend radius, because this is 16th material with the tooling that Stellar Robotics uses, that'll give us a bend radius of 0.039. 90-degree angle is fine. Click OK. Alright, so now we need a hole for the gearbox shaft. So let's create a sketch on this face here. Now we know it's going to be centered left to right, and we know it's going to be 1 inch up from the bottom. So what we're going to do is what we've done before is we're going to turn on construction geometry. We're going to pick project geometry. We're going to project the bottom edge of this flange. We're going to leave construction geometry on, pick a line, find the center point of the line, go up the distance that we want, type in 1 inch, and press enter. Alright, so next we're going to place a center point at the end of that line, and that will give us a centered hole left to right and offset from the bottom the distance that we want. So finish the sketch, click on the hole feature. Now this whole dialog also changed in Inventor 2019. I imagine you guys can figure it out. We talked about that a little bit in an earlier video. Alright, so termination is going to be Distance is actually fine in this case because it should automatically take it through the thickness as we see here. The diameter is going to go ahead, we're going to go ahead and use the bearing hole size, just that's a good standard size to use, so it's going to be 1.125, and then click OK. Now, we also need to put mounting holes in here because this is what the gearbox is actually going to be attaching to. So we talked briefly about the gearbox mounting pattern before, and we used it on this bearing block because we like to standardize to this whole pattern where we can. So it's a square bolt pattern on a 2-inch bolt circle, 2 inches in diameter. Same as the plate here. Now there's only 2 holes on the gearbox, but they're arranged in a square because you can rotate the gearbox. So they're kind of at a 45-degree angle rather than 2 holes horizontally 2 inches apart. That's a bad way to explain that. But either way, we're going to put 4 holes in just like we did for the bearing block, just in case we want to turn the gearbox 90 degrees. If these like motor prongs needed to be turned, it's just convenient to add 4 holes. It removes weight. It doesn't cost us anything to add 2 holes that we don't use. And it gives a little flexibility and consistency in our design. So that's what we're going to do. So we're going to create another sketch. We're going to click on the same face again. We need to project this hole so we can get access to the center point. So we're going to turn on construction geometry, click project geometry, click on the hole, press escape. We're going to leave construction geometry on because we got to draw the bolt pattern, work geometry. So using the center point that we just projected, we're going to create a circle. It'll be a construction circle. So we're going to make that 2 inches in diameter. This represents the bolt circle. Oops. Next, we're going to use a square. This is just like we did with the bearing block. We're going to use a center point, 2-point rectangle. We're going to start at the center point of this circle. We're going to attach the corner of the rectangle to the circle at somewhere. Then what we're going to do is we're going to make the 2 sides of the square equal using the equals constraint. That'll make a square. So click the equals constraint, click one side of the square, or one side of the rectangle and the other side of the rectangle. Alright, then we're going to place center points at each of the 4 corners of that square. And finish the sketch. And go to the hole feature. And we're going to set our diameter to be 0.2. Actually, no. What am I doing? We're going to use a clearance hole. It'll be the same size, but click on clearance hole. Wait for it to load a million years because I restarted my computer. Alright. Sometimes I get sloppy and I just type in the dimensions for common hole sizes because I've memorized them. I try not to, but sometimes it's just faster to type in the screw hole size if you know it. That being said, it's good practice to use these presets if they apply in your case. So you'll see that the diameter for a clearance hole for a number 10 fastener is 0.201. That's standard. So sometimes I just type in 0.201 in the whole dialog without actually clicking on this clearance hole thing. But kind of personal preference, this is best practice what we did here though. So click OK. Alright, so we're done with this for now, so we're going to go ahead and give it a save and give it the next number, which is 6. Alright, so next, now we don't have any mounting holes here because we're going to do those later, but let's go ahead and place it in our assembly here and constrain it in place. So click place, find our part, open. Oh, I forgot to set the material. Okay, so we're going to rotate this once by the x-axis. We need to go more and one more time. Alright, that's the orientation it should be in. And real quick, because I messed up, we're going to go back. We're going to go to material, up to aluminum 5052H38. And change the appearance because I want aluminum flat. Give it a save. And leave it open because we're going to do some more work on it. Okay, so first of all, we know that the bottom side here mounts to the top of this structure. So let's constrain that using a mate constraint. Bottom of that to the top of that, apply. We also know that the center of this hole is to be on the center of the gearbox. So let's constrain center line of that hole to this work axis here. Apply. Now this can only slide back and forth, and we know that we want this top bracket to mount to the face of the gearbox. So let's constrain that using a make constraint as well, and click apply. Alright, so you'll notice this is 1/8 of an inch set back from the structure, which kind of looks nice and gets rid of some unnecessary material and potential sharp edges. So let's go ahead and, well, actually let me back up on that. Alright, so we're going to have to model a different part for the bottom. It'll be very, very similar, but it'll be a 1/16 of an inch shorter at the at this like length dimension here, and that's because it has to go inside of this one. Now we could use the same part, but there's going to be some mounting holes up here where this gearbox mounting bracket interfaces with the structural parts, and the holes would be shifted on the bottom, and I don't want to deal with that. So we're just going to model a different part that's a 1/16 inch shorter. And in reality, what we're going to do is we're going to just do a save as on this part. So let's do a little more work on this part so that when we do the save as, we don't have to do that work for 2 parts. We can do it just for 1. So basically, when we have our bottom part in here, we're going to have kind of this box feature here, right? So we're going to have the bracket in like this. And if this motor's fairly heavy, there's going to be some weight on this. This plate is pretty thin, and with vibrations and shock loads as the robot, goes over bumps and runs into other robots, this gearbox is going to want to bounce up and down, and this bracket is thin enough that they're going to flex, and so this whole thing is going to kind of be able to bounce up and down, and it might be able to angle a little bit, and it's just not going to be what we want. So we want to be able to prevent this bracket from bending up and down so that it's more rigid. Now we're going to do that pretty simply by adding just some small flanges, just some small bends here on either side, and that'll add a lot of rigidity. So let's go back to this part here. Remember that this face is the top. We're going to just add a little flange on this side and a little flange on this side just sticking out, just to act as a stiffener. I'll talk about a little bit more about that in a second. So let's go to flange. Let's click on this edge and this edge. Now, first of all, it keeps our old settings. We don't want them to be this tall. We're going to go 1/2 inch. That's getting close to the smallest flange we can form in this material. I think we can form 3/8. Actually, we're going to do that. The difference between 3/8 and 1/2 inch in terms of strength is very, very slight, and 3/8 just takes up less space and it looks better. So in addition to that, we want these flanges just to stick on the outside. They're not really there for any particularly precise mounting surface. They really don't serve any purpose other than stiffening the part. So we're going to change the bend position, which is going to be this guy right here, bend from adjacent face. And basically that just puts the bends on the outside of whatever edge you selected. So that's fine for our case. Now keep in mind, if we change the bend radius and make it like 1/4 inch, that moves the flange out. So you've got to understand that if you use this bend from adjacent face option, the position of the flange, like left to right in this view, depends on your bend radius, which is usually a bad thing. But in this particular case, because these are just stiffening flanges and there aren't going to be any like bolt holes or anything that have to match up with something else, we're okay. Alright, so in addition, we need to change our height datum to bend from the intersection of the 2 outer faces so that our height datum is measured from the bottom here to the end of the flange rather than the inside here to the end of the flange. So let's change that. It makes them a little shorter, which is okay. We can still bend them. And I typed in my bend radius wrong. It's supposed to be 0.039. Okay, I'm happy with that, so click OK. Alright, so this is the thing about sheet metal. Sheet metal, your strength does not come from material thickness. So if you're making your robot out of you know, machined aluminum or something like that, your strength is just going to come from large blocks of aluminum that you machine to the shape you want. With sheet metal, you're using very, very thin metal. I mean, a flat piece of 16th inch aluminum you can bend with 4 fingers, right? You can hold it finger, thumb in either hand and bend it really easily. It's very thin and it's not very strong. But as soon as you put a flange on it, right, as soon as you bend it, you can't bend across this bend hardly at all. And so the more bends you put, and if you put them in places that are strategic and they're in the right place to make a difference in terms of strength, your parts can be very, very strong while still being made out of very thin aluminum, which is light. So with sheet metal, you have a lot of control over exactly where you put your material, which is the really big advantage of sheet metal over using, for instance, box tubing and brackets, which is what a lot of FRC teams use. Box tubing and brackets are easier to design, and they require less advanced machining. You know, for sheet metal requires a laser cutter or a plasma cutter or a water jet cutter and a press brake. But if you have access to sheet metal working tools, you can give yourself a lot of control over exactly where you're putting your weight, and you can get very strong parts that don't weigh very much. So that's the reason for adding these flanges. They add very, very little weight, but they really strengthen this part. So what we're going to do is just, in the interest of saving ourselves some work later, because we're going to copy this part, change the dimension a little bit, and put it on the bottom, we're going to kind of finish this up. We're going to add a few preliminary mounting holes here. We will probably have to change their dimensions later. We're going to just add a row of holes, and we'll worry about positioning them correctly later. We're also going to radius some of the corners and stuff. So let's go back to this part. Let's create a sketch. And we're just going to create a construction line that is 1.5 inches. I don't think that's right. No, it needs to be 1 inch. Then we're going to use a vertical constraint from the center point of this line to the origin. I'm just using this line to position centers for the holes. Then we're going to dimension from this dotted line to here, and this will be 0.375. Basically, this is 1 inch wide, so it's going to be 1/2 inch from the end here, but this is already 1/8 of an inch in from the end, so 1/2 inch minus 1/8 is 3/8. All right, then we're just going to put one point here at the end, and we're going to use a pattern to pattern the holes across. There's only going to be 3 of them to start. I think we're going to have to end up going with 4 or something, and this whole pattern is definitely going to shift left to right, so we're going to edit this later, but probably not in this video. So finish the sketch, create the hole. This is going to be just a normal plain hole, and it's going to be 0.196 because these are going to be rivets. So click OK. Then go to the rectangular pattern feature, click on the hole, go to direction 1, click on the arrow, click a line running across the part in this direction. That one works. It's going to be 1/2 inch spacing, and we're going to start with 3 holes. Like I said, we're definitely going to have to move these later. However, for now, this is what we're going to do. So click OK. This part is not going to end up being symmetrical left to right when we're done with it, and that'll become apparent later. So we'll get to that. So next, we're going to add some nice big 1/4 inch fillets down here. The sheet metal tool uses this corner round feature rather than the 3D model fillet. This corner round tool is a little bit smarter for sheet metal parts. The default radius is 0.25 inches, so that's what we want. So click on this corner and that corner and click OK. Then we're going to add some smaller radiuses here just to get rid of sharp corners. So we're going to corner round. We're going to change the radius to 1/8 of an inch. Click on, once you change this, you need to click back on 0 selected so that it gives you this arrow symbol here. And then click these 4 corners to round those off and click OK. Alright, so this part's pretty much done. So we're going to give it a save. Everything looks okay here. Like we talked about, this is an extra hole, but it's not hurting anything, so we're going to leave it there. Alright, so now we're going to do a file save as on this part. We're going to give it a new number. And then we're basically just going to shorten the base sketch by 1/16 of an inch so that this flange will be inside this one, and we're just going to put in the assembly. So really easy. There's a reason that we added all these holes and the fillets and stuff before we did the save as, because otherwise we would have had to just do them twice on two different parts that were essentially identical. So let's go to face 1 and edit the sketch, and let's edit this length dimension here and add a minus 0.0625 to the end of the equation. Press enter to get out of that, and then finish the sketch. You'll see the part updates and shortens a little bit. I'm going to go to the home view and give this a save, and I'm just going to go ahead and close it. All right, so then we're gonna place the component, drop it into this assembly. I'm going to rotate once by the x-axis, and then I'm going to rotate twice by the z-axis to spin this around. All right, so let's go to the constraint tool, constrain the inside of this part to the bottom of the structure. Then we need to escape out of that, move this to a place where we can grab it. We're going to constrain the center line of this hole. Actually, no, we're not. We're going to constrain this face to the inside of this existing bracket, and then we're just going to use the flush constraint to line these two sides up. There's no reason to constrain the center point if we don't have to. So we're going to go to the flush constraint. We're going to go to the side of this bracket and the side of that bracket and line them up. Okay, so that's a pretty strong structure. Plenty of mounting places for the gearbox. Getting this assembled could be a bit tricky. That's always the issue, is looking at assemblability. I think ideally you would want to just screw these two plates to the gearbox first, then slide the gearbox on with the pulley and all that stuff and put these rivets in. I'm trying to think if there would be a better way to do this that would be more accessible, because if you need to take this gearbox off, you know, this can be kind of a pain. Now, that being said, unless you screw up a pulley or break a belt or something, you don't need to take this gearbox off, because the new VersaPlanetary gearboxes come apart from the back. So even if you need to change gear sets, or if you strip a gear out or something like that, you can take the whole gearbox apart from the back while leaving this front block and the output shaft in place, so that the gearbox is maintainable without actually removing it from these brackets. So access to these screws isn't super critical. We're not going to worry about it a whole lot for our application, but it's definitely something to be considering when you're designing something. You want to make sure it can be put together and taken apart fairly easily. In this case, you know, these rivets are pretty easy to drill out. In a lot of cases, it's faster to drill out a rivet than it is to undo a screw. So I'm perfectly comfortable, if we need to take this apart, just drilling out these rivets and pulling this whole thing off. At a competition, that would be a perfectly acceptable solution. So we're going to leave this alone for now. We're going to finish modeling some drive components and end the video with that. And then the next video, we're going to go in and start adding mounting holes and finishing up parts. That should be good. So let's go to the home view here and give this a save. All right, so the next thing we're going to do to finish off our gearbox part here is we're going to add a shaft collar. Now, looking at this, we've got this hole here. We want to make sure this hole is big enough that if we put a shaft collar on this shaft, that it won't interfere. So we might have to make this hole bigger if it's not big enough. I think it will be. But Vex Pro sells some pretty nifty shaft collars, little metal pieces that basically clamp on the shaft that keeps this pulley from being able to move side to side. So it's going to be a spacer in here, then the pulley, then a shaft collar to hold it on, and then this extra shaft out here is just extra. You could cut the shaft off if you wanted. You could even cut the shaft off right at the pulley and then tap a hole in the end and put a washer and a screw, kind of like the roller shaft here. You could do something like that. However, in a lot of cases, you know, you're gonna build a robot for one season. At the end of that season, that robot's gonna get taken apart, or certain parts are gonna get removed from it. VersaPlanetary is being one of them. So typically, you don't want to do any cutting of your VersaPlanetary shafts if you can help it, because you can reuse that gearbox and that shaft the next year, and the next year you might not want that shaft cut down short. You might need it left long. So we try to avoid cutting these shafts if at all possible, just to maintain reusability. So we're just going to go and get the CAD model for this shaft collar. So we're going to go to Vex's website here. It's under Hardware, under Clamping Shaft Collars. We're going to scroll down to CAD Files, and it's going to be Clamping Shaft Collar 1/2 inch hex ID. So download that file, right-click Show in Folder, cut that out of there, go to our drum roller project folder, paste it in there, go back to Inventor, open the step file to import it, wait for it to load, click OK, delete the sketch. Alright, so essentially you've got a screw here and then this tapped portion over here, and you've got this split in the collar. So you put the hex shaft in here, and this hex is pretty loose, and then you tighten the screw down and it flexes the aluminum here and starts to close this little gap, and it tightens down on the hex shaft and holds it in place. Once you tighten these down, they don't come off. You have to loosen the screw in order to slide it off the end of the shaft. So they do a pretty good job of holding things in place. And they're also very, very small. This is only 1/4 inch thick. And then we need to check the outside diameter here. Measure. So it's 1/2 inch radius, so it's 1 inch in diameter. And this hole in here is 1 1/8 inch. Yep. So this hole's big enough. It'll be a little close, but there's nothing sticking out here other than that little corner, but that's not enough to be an issue. So let's set the material to aluminum 6061. Change the appearance to aluminum. Actually, no, it's anodized black. So we're going to go glossy black is the color I used for black anodization. We're going to set a work axis in the middle for constraining, and then we're going to give this a save. Close it. Alright, come back to our assembly here, place component, shaft collar, place 1 down, hit escape, C key for constrain, and gonna use this center line here to constrain the center line of the shaft collar to the center line of the gearbox shaft. Apply. Then we're just going to constrain one side of the shaft collar. The shaft collar is reversible, so which way it's facing doesn't matter. So we're going to constrain this face of the shaft collar just to the end of the hub of the pulley. Alright, so that clears. It's just barely flush on the inside. This hole here acts as clearance. That works out really nicely. And then, like we said earlier, there's going to be a spacer in here, which we'll add at a later date. Okay, so we're done with the gearbox for now. We'll come back in the next video and add mounting holes and stuff, but let's finish up our drive components and then end the video here. So we're going to model the tube that goes across here. So this end cap is fixed in place. It can rotate, but we're not worried about that. And this end cap's fixed in place, so we're just going to measure the length from under the flanges and model a piece of tubing and then put it in the assembly. So use the measure tool with the M key, measure from under the flange here to under the flange here. It is 20.75. Okay, so we're going to go make a new standard part, create. Alright, so the outside diameter of that tubing is 1.25. Now this tubing is tubing that I sell from CRP, so you would buy it. I have the tubing specifically sized for the end caps, so the tubing that comes from CRP is tolerance to fit the end caps correctly. So 1.25 outside diameter, and then we're going to use the offset tool, and the wall thickness is 0.065. Now that makes the inside diameter of the tubing nominally 1.120. If we go look at the end cap is 1.125. So basically there's 0.005 of interference. So this, when you press the tube, or when you press the end cap into the tube, there's a 0.005 of interference fit actually it's 2.5 thousandths all the way around, which means there's a 5 thousandths overlap in the diameter. But it's actually a 2.5 thousandths press fit, which means that these end caps don't need any fastening method other than the press fit to hold them in place. We've used these for winch drums on Stellar Robotics in 2016 with our PTO climber lifting 150 pounds of robot with bumpers and battery up, at a pretty solid rate, and these end caps don't slip, they don't pop out, as long as you've got spacers on both sides. If you're not constraining the end, under load they can come off. But as long as you got like a shaft collar on each end, they can't slip, they can't rotate. So that's good. So finish the sketch and extrude this out, and it's 20.75. And I'm going to do what I usually do and go symmetric and put it in the middle. And we'll click OK. The material for this is aluminum 6061. Set the aluminum flat. Okay, so give this a save. We'll give it the next number in the series, which is 8. Then we're going to close this because we're done with it. Place it in the assembly part. Place one down, press escape. Go to the constraint tool. I didn't place a centerline axis. I probably should have, but I'm just going to use the cylindrical surface of the tube. That should be fine. All right, so we're going to constrain the cylindrical surface of the tube to the work axis of the work axis of the shaft. Click apply. Then we're just going to constrain one end of this tube to the inside of the flange of one of these end caps. It could be either one, but we're just going to use this one. Click apply. Alright, so you'll notice the outside diameter of this flange is the same as the outside diameter of the tubing. There's a little bevel here, but don't worry about that. That's just for deburring purposes in the manufacturing of the end caps. And the end caps are nicely pressed into the end. It lines up on both sides. That's good. Alright, so now what we're going to do is we're going to model, so that this tube was 20.75. We're going to model a piece of rubber that goes over this. Basically, there's a rubber tubing that you would stretch over this roller that would act as a gripping surface to grip the game pieces. We're just going to model that and put it in the assembly just for the sake of accuracy. So this was 20 3/4 of an inch long. We're just going to make our rubber 20 inches long just for simplicity. So let's create a new standard part. It's going to be the inside diameter of the roller, or the rubber, is going to be the same as the roller, which is 1.25 inches. And the rubber is going to be 0.25 inches thick, so we're going to offset this by 0.25. It's 1/4 of an inch. We're going to finish that sketch. Extrude this region 20 inches, symmetric. Click OK. Alright, so the material is going to be, rubber. Not going to create a work axis or anything. Probably should, but I'm not going to. Click Save. Give it the next number in the series. Go back to our assembly. Place component. Grab the rubber. Place it in. Press Escape. Use the C key to bring up the constraint tool. Select the cylindrical surface of the rubber sleeve, center line of the shaft, and then basically what we want to do is we want to center this left to right. So we've got we're just going to use a flush constraint from the end of the end cap. So the tube itself is 20 3/4, and then we've got an extra 16th here for this flange, and an extra 16th here for this flange. So that gives us 7/8 of an inch, or 20 7/8 of an inch. This is 20 inches, so we've got basically 7/8 of an inch. This drum roller is 7/8 of an inch longer than our rubber, so we've got to divide that 7/8 of an inch up between this side and this side, basically. So basically, if it's 7/8 of an inch longer than the rubber, we need to take that 7/8 of an inch and split it up evenly on each side to center the rubber. So half of 7/8 is 7/16. And so we're going to go to the Constraint tool. We're going to click the Flush tool. We're going to click this one first. Has to be the rubber first, then the end cap flange. And we're going to type in 0.4375, which is 7/16. You can also type in 7 divided by 16 if that works for you. And click OK. Now if we go to the measure tool with the M key, we can go back to the other side, try to get an angle where we can measure the end cap to the rubber, and we can see that it's the same 0.43, and then it's rounded to 8, but it's 0.4375. If we change our precision to 4 digits, we can see. Okay, so this is what the rubber, or this is what the roller would actually look like on an actual robot. You can see that it's not touching the gearbox. It's a little close on this bracket here, but nowhere near actually interfering. I'm happy with that. Alright, so that's going to be it for this video. In the next video, we're going to start adding all the mounting holes. We're going to take some of these large flat places and we're going to do some lightning holes just for the sake of practice. The video after that, once we add all the holes and lightning features, the video after that we'll go through and add spacers, fasteners, basically everything except rivets, which should be not too bad. So thank you for watching. I'll see you in the next one.